So, let us now start the next topic on module 2, which is existence and uniqueness of solutions. Okay, given here what we are going to see is whether if you're given a differential equation, whether it is linear or non-linear with an initial condition, this in fact is an initial value problem. I'll write it as IVP, initial value problem, where the initial conditions are given at t0 is equal to a. See here what you have to understand here is f, we are taking the derivative with respect to x. This can contain terms with t as well as x. T is a dependent variable, t is independent variable and x is a dependent variable. Okay, so now the question is if you are given any set of equations like this or ODEs like this, the question is, does there exist a solution for this to this initial value problem? That means can we find out a solution for this initial value problem, and if at all we can find a solution, then is it unique? That is a question that we have to answer. Okay, so now the conditions for existence and the uniqueness are stated here. So the condition there is a sufficient condition for existence, which is stated like this: if the function f, the given function f is continuous near a comma b, then the solution exists for the initial value problem. Similarly, for uniqueness, what do you mean? That if the function, if the derivative of the function with respect to the dependent variable dou f by dou x is continuous near a comma b, then the solution to the initial value problem is unique. Okay, for example, if you are given x dot is equal to 2x at x is equal to x at t0 is equal to 1. X at t0 is equal to 1. So what is the solution to this? X dot is equal to 2x. We know x of t is equal to e raised to 2t, right? E raised to 2t plus c. So I can say that at t equal to 0, I will write it as c e raised to 2t, c e raised to 2t. At t equal to 0, I can take this as 1. So the solution would be something like this, e raised to 2t or something like this. So what happens for this, if the initial conditions are given, I can get a unique solution here. This is the only solution for this equation, right? This is the only solution for this kind of an equation. But if the initial conditions are not given, I can plug in any kind of C to get infinite number of solutions for this. And there can be equations where I may not get a solution also. And if I don't get a solution, I need not think about the uniqueness. And next thing is, I may get a solution for the system, but the solutions may not be unique. I can have different solutions for the system, even if the initial conditions are given for the same solutions for the system. Okay, now we will see continuity, what is meant by continuity, and also what is meant by differentiability, and also we will go and see some statements about continuity and differentiability. Okay, so this is only an introductory class, a little bit of math to introduce you to the main topic on existence and uniqueness of solutions. Okay, so if you look at this function, what can you say? This function is continuous, as it is seen that at every instant of time we have the values of x and also f of x or f of x. So this is a continuous function. This, we have a discontinuity here. This is not a continuous function. Here there is definitely discontinuities between the functions. So this is not continuous. This in fact is continuous. This is continuous. This is also continuous. Okay. So this is how we, looking at the function, we can also say that whether the function is continuous or not. But if we are not able to plot the function, without plotting, how to see whether the function is continuous or not. Okay, I will write here continuity here. What is continuity? I will write here a function f is said to be continuous if for every value of c in its domain D, f of c is defined and the limit x tending to c, f of x is equal to f of c. That is, the limit of f of x as x approaches c in either directions is f of c. So I will explain this condition in this statement using example. Okay, so for this function I will draw it here. This is 2 For x less than 1, it is 2 for x less than 1, and it is x squared for x greater than 1. So something like this. Okay, something like this. This is 1 at this point. Okay, so what does the statement say? This is x. Let this be x, this be x, and let this be f of x. What does the statement say? If I travel along this domain x, I am going to travel along this domain x, and I have some point C on this domain x, and at every point C on this domain x, whether I approach C in this direction or in this direction, at every point this limit should exist. That means the limit x tending to C, x can tend to C in both directions. X can come to C like this, x can come to C like this. Okay, so f of x, it is defined, means this should exist. It should exist. Exist means it should not be an unbounded value, it should be a bounded value, and it should be exactly equal to f of C. So here there is a confusion here. What will be this value? Whether is it 2 or 1? So we can say that it is not the same. Here it is not the same. It is not equal to f of C. So when I approach it from this direction, it has a different value. It is 1. When I approach it from this direction, it has a value 2. So it is not the same always. So x is equal to C. From minus x to C, f of x is equal to 2. Then limit from x to C, f of x is equal to 1. So there is no, what happens here? These two, we have two different limit points here. So the limit of f of x as x approaches C in either directions is f of C. Should be the same also. Then we can say that the function is continuous. Given function is continuous. And if the given function is continuous, then we can say that, what can we say? We can say that the function, the given equation f of t comma x has a solution. It has a solution. That means a solution exists for the system. Okay, so that is about this example, and this is the general definition for continuity. Okay, we will see what is differentiability. Okay, a function f is said to be differentiable if for every value of C in its domain, limit x to C, in order to see what differentiability is, this is the definition for differentiability. For that we will see an example here. I will draw a curve here, something like this. So let me mark the point here C as C, and let me take a small distance, very small distance. Even though I am drawing it as a bigger one, it is actually a small distance. So in order to get accurate results, we have to take h as very small, h tends to 0 to get the accurate results. So what is this? We have to take the slope of this curve. That is what is happening here. F of C plus h minus f of C divided by h, right? So the limit of this exists. That means the slope should be there. The limit of this exists, and it should be finite. What does it mean? It should be finite. That means if what happens here is it should be finite. Then we can say that the function is differentiable. Okay, the function is differentiable. Okay, so this is about differentiability. So we will see some examples for this differentiability and also for continuity, so that we will get a more better intuition into continuity and differentiability. So what about this function f of t comma x, like this kind of a function, whether it is continuous or not? Okay, for that, let us see. For continuity, I can write here. For continuity, what was the definition here? For continuity, I can write here, limit x tends to C, f of x should be equal to f of a in both directions, right? So this implies, so I can take f of C, C. So this is limit x tends to C is equal to x squared c squared plus 2c plus 3. If I approach it through x, if it comes to c in any direction, this will have the same value. So the function is continuous. Okay, this function is continuous. So I can say that solution exists for this system. Solution exists. Okay, exists for this system. Solution exists for this. We know how to, we can integrate this function and then we can find a solution for this kind of a system. Okay, what about dou f by dou x? What about differentiability? Dou f by dou x. Dou f by dou x, we have to see whether dou f by dou x is, this is differentiability, and we can see if this exists or not. We need not have to check much into this. Without that, we will try to see whether this also exists. So what is dou f by dou x? It is 2x plus 2. 2x plus 2. So we definitely know that this function is definitely continuous function. So this is also continuous. Okay, here we can check it using the same rule here. This is also continuous. So we can say that continuous. So we can say that the solution is unique. So this both conditions are satisfied. That is, for continuity we have to check the existence we have to check the continuity of f. For uniqueness we have to check the continuity of dou f by dou x. Here both are continuous. We can say that solution exists as well as it is unique. Okay, so now we will go and see the next equation. Places some vacant here. I will give you one example here. X of t comma x is equal to t squared x squared. Okay, you can check this. Okay, you can check the continuity of this function. Okay, you can check whether f is continuous, and also dou f by dou x is also continuous for the system. Okay, and then we will later on check whether this function has a unique solution or whether solution exists and if it is unique. Okay, so now here you have this function. So this is mod x function. So it is something like this. Definitely this one like this. So this is continuous, right? This function is continuous. We have no doubt about that. So whether we approach it, I can write it here. X tends to c, limit x tends to c of f of x is equal to x mod x, limit x tends to c of mod x, limit x tends to c of mod x, definitely will have the same value only. So whatever condition. So this is continuous function. This is a continuous function. Okay, so now we will check whether the derivative is continuous. We will check whether dou f by dou x is continuous now for this function. Okay, whether dou f by dou x is continuous. So for that, what we will do here is we will take this thing, like what we have to take here, the previous system equation here, f of c plus h minus f of c. Okay, so we will take that and see whether this is continuous or not. Okay, so this says that limit h tending to 0 of c plus h minus c by h. Okay, so when c is equal to 0, at 0 let us see what happens. At 0, at c equal to 0, there is definitely, you all might be knowing that there is definitely a discontinuity at this point. This implies that limit h tends to 0 of h minus 0 by h is equal to limit h tends to 0 of h by h, right? H tends to 0 of h. So what, when I approach it from the left side, limit h tends to 0 minus, like I'm approaching it from the left side. So this becomes equal to minus 1. So this term will be equal to limit by h will be equal to minus 1, right? So if I approach it from the right side, limit, that means h is increasing in this direction. If I approach it in the opposite direction, it would be minus h. So it would be something like this: h limit h tends to 0 plus by h is equal to plus 1. So here what happens, the limits are different on either sides, so the limit does not exist here. So the limit doesn't exist here. So here what we can say, that here for this system, this dou f by dou x is not continuous. Okay, we will come to that later, whether the solution is not unique or not. Definitely we have a unique solution for this, but even if that is what we were discussing earlier, we will come to that. Okay, so this is about continuity and differentiability. So this is another problem that you can try out and see whether this function is continuous and the derivative of the function with respect to x is continuous or not. You can do this problem also. Okay, so you have two problems to work out. Okay, so now I will revisit what I have said here. So the sufficient condition for existence and sufficient condition for uniqueness. Okay, so we saw that here in this previous case here, the function is continuous. This function is for continuity, f is continuous, and for this case dou f by dou x is not continuous. So if f is continuous, I can say that solution exists. Suddenly I can say that solution exists for the system. So it is sufficient. So that means continuity of f is sufficient to say that solution exists. But now dou f by dou x is not continuous. That means does it mean that the solution is not unique? No. Here we cannot say anything. That is why it is only a sufficient. We cannot say anything about the uniqueness of the system. Okay, about uniqueness, we cannot say anything about uniqueness. So that is why this dou f by dou x continuity and f of x continuity are only sufficient conditions for existence and uniqueness. So that is why the sufficient conditions are given here. If I don't get that dou f by dou x is continuous near a b, then I cannot say anything about, I cannot conclude anything about the uniqueness of the system. The system may have uniqueness solution, but if it is continuous, directly I can say that system has unique solution. Okay, so that is the meaning of sufficient conditions. Okay, that means it is not necessary to be continuous for a system to have a unique solution. Okay, so these are the conditions. What are the two conditions? I will just repeat it once again. The conditions for a system to have given any initial value problem to have a solution is that the given function should be continuous, and to have a unique solution, the function the partial derivative of f with respect to x should be continuous. So these are the conditions for uniqueness and existence. So we will state it in the form of a theorem here. So this is a theorem here, which is again stated is in this form, in a very formal form. That means suppose f of t comma x is a continuous function. That means I am saying that f of t comma x is a continuous function in some region D defined by a less than b less than d. That means here this is the region, this is t and this is x, and f is somewhere here. F is a function of t and x here. So in t lies between a and b, and x we have chosen a region x lying between c and d. we have chosen this rectangular region here, okay. So here in this region we are saying that if f of x is a continuous function in the region D defined by this domain, in this domain, if I have a function f of x which is continuous in this domain, then, and if t0 comma x0 is the initial point of the system, t0 and x0 are the initial points of the system, t0 and x0 are the initial points of the system, then there exists an epsilon greater than 0 and a function xt defined for t0 minus epsilon less than t0 plus epsilon, that is a solution to the initial value problem defined by equation 1. So what is the last part of the sentence say? That means if the function is continuous inside this rectangle in some domain, like this, then if I get a continuous solution, then there exists a region epsilon greater than 0 where I can choose some t0 less than epsilon and t0 plus epsilon, where region for this function where I can get the existence of the solution. So this existence is said in a very local area. That means it is always said in the neighborhood of the domain, near to the initial value. That means near to the initial value I can say that the solution exists for the system. It is not spoken in terms of globally. It is spoken in the local sense. So that is why it is said that near to t less than epsilon and t plus t0 plus epsilon, near to a very close region near to t0, if this function is continuous, I can say that near this region the solution for this equation exists. Solution for our equation x dot is equal to, this is the equation x dot is equal to f of t comma x with x at t0 is equal to some b, something like that, x0. So x at t0 is some x0, then this solution exists. So what is the uniqueness theorem? In the same way we can state the uniqueness theorem. If dou f by dou x is continuous in this region, then very near to this t0 plus epsilon and t0 minus epsilon, I can say that I have a unique solution for this equation. So that is what is meant by this uniqueness theorem. So these are the statements for existence and uniqueness theorem which you have to see thoroughly. So though we spoke in terms of the sufficient conditions and about existence and uniqueness, this is said in the reverse way around, because here we are saying that if f of ts is continuous, and here we are saying that dou f by dou x are both continuous. The f of tx is continuous, has to be continuous for dou f by dou x to be continuous functions. Okay, so then we have the unique solution for the initial value problem. Okay, so now we will see some problems here to check the existence and uniqueness of these solutions. Okay, so what is this? For existence, what we can see, we have to check for f of t comma x, okay, at x0, f of t comma x at x0 at t0 comma x0. So here if I substitute it at t0 comma x0 at t0, this function for if you look at this function, we can say that this function is always continuous. This has some value except at t0 not equal to 0. If t0 equal to 0, what happens? This goes to infinity. So we can say that this function is continuous everywhere other than at t0 equal to 0. Okay, so if you are given some t0 equal to 0, then we are done. We will not be able to find a solution for the system. Okay, so now this we can state here is it is continuous everywhere. Continuous everywhere other than t0 equal to 0. t0 not equal to 0. And also if in all those places where it is continuous, we can say that the solution exists. Solution exists in those regions. Okay, x is there. Okay, the next condition is dou f by dou x. Dou f by dou x for t comma x. What is dou f by dou x? Dou f by dou x is 1 by t, and it is dou f by dou x is 1 by t. So what about this dou f by dou x? This also is continuous for t0 not equal to 0. So this also is continuous for t0 not equal to 0. Continuous for t0 not equal to 0. For this case also, what we can say is, we can say that the function is continuous for t0 not equal to 0. We have a unique solution here. Solution here for all t not equal to 0. Okay, so this is about the uniqueness and uniqueness and existence of this equation. Okay, so we will go to the next part. Next one, 3x raised to 2 by 3. So here we can see f of x comma t, f of t comma x is equal to 3 into x raised to 2 by 3. Okay, so whatever value of x we plug in here, anyway this function will have a value. Okay, this is continuous. This is a continuous function. This is a continuous function. This the limit exists, and this is a continuous function. So the solution exists for this. Okay, solution exists here. So now what about the next one? F of dou f by this is dou f by dou x. Okay, what is dou f by dou x? It is 3 into 2 by 3 x raised to 2 by 3 minus 1. So what will it be? That is 2 x raised to minus 1 by 3. That means 2 by x raised to 3, right? 2x cube, right? 2x cube. So what can you say about this? What can you say about this? If it is 2x cube, what can you say about this? So this function is not continuous, right? This function is not continuous at x is equal to 0. So not continuous at x equal to 0. It is not continuous at x is equal to 0. So what can you say? That solution, we cannot, since it is not continuous at x is equal to 0, we cannot say about the, we cannot say anything about the uniqueness of the solutions. Okay, uniqueness of the solution at x is equal to 0. But we can say that the solution exists, but we cannot say anything about the uniqueness of the solution at x is equal to 0. Okay. So now we will see the next problem here. T x minus 3. This is a nice problem here. So here we can say that f of x comma y is x into this is 4 root of x minus 3. This is x is 3 minus 3. So this is t. This is 4 into t minus 3. I can give it as 4 into root 0. So this is 0. So near the point 4 and 3, we can say that f of x comma y is continuous. So we are speaking about continuity only near the initial points, like near the points where the initial conditions are given. So near this point, we can say that the function is continuous. So solution exists for the system. Solution exists. So what about dou f by dou x? What about dou f by dou x? Dou f by dou x is something like t by 2 root x minus 3, right? 2 root x minus 3, right? 2 root x minus 3. So now at x is equal to 3, what happens? At x is equal to 3, what will happen? X is equal to 3. x is equal to 3. At x at the initial condition, what happens? The dou f by dou x is infinity. Dou f by dou x is infinity. That means the limit x does not exist here. Doesn't exist here. So we cannot say anything about this situation. Doesn't exist here. Okay. So here can we say, that means the system, this equation is not continuous here. It is not continuous here. Can we say anything about the continuity, about the uniqueness of the solution? No. That means we cannot say anything about, that means we cannot conclude. I will write, we cannot conclude anything about uniqueness. Okay, so this is this equation. So we will go to another interesting example here, which we can see here, the same problem but with different value, different initial condition. So here we can say that near this initial condition, I cannot say conclude anything about the uniqueness of the system, because I got this as not continuous. Okay, so we will go to the same kind of example here with a different initial condition. Okay, so here I have this function definitely is continuous. So I will just take f of t comma x is equal to t into square root of x minus 3 is you plug in t equal to minus 2 and x is equal to 20. So this is continuous here. Continuous, I can say that the function is continuous near at x is equal to minus 2, at t equal to minus 2, or near the initial conditions here. And what about dou f by dou x? So since the function is continuous, I can go to the next step. If it is not continuous, I need not bother about the next step, right? So here dou f by dou x here. So here I got it as t by 2 root x minus 3 here, So t is minus 2 by 2 into root 20 minus 3. Oh god, this is in fact continuous. So this has a finite value here. And so what can we say, that here near this initial condition here, near the interval minus 2 and 20 here, so here near this interval, nearby to this interval, we can say that the function is continuous, and we can say that this initial value problem has a unique solution. But about this previous initial value problem, I cannot say anything about the uniqueness of the solution. But here I can say that since I got this as continuous near this initial values, I can say that I have a unique solution here. Here the solution exists. Okay, so we will do some problems after this. So in the next class we will continue with the same uniqueness and existence theorem, but we will try to state it in using a different method. So it will be on the same lines only, but it will be something we will look at it through Lipschitz constant. Okay, so this is